Case study: Kobe earthquake and soil liquefaction. Welcome back to Blueprint to Reality, the channel where we break down the hidden forces that shape engineering and the built environment. Today, we're revisiting one of the most devastating earthquakes of the late 20th century, the 1995 Kobe earthquake in Japan. While the magnitude of the quake was powerful, much of the destruction was caused not by the shaking itself, but by something happening beneath the surface: soil liquefaction. In this case study, we'll explore what happened in Kobe, why soil liquefaction played such a big role, and the lessons engineers have taken from this tragedy. The Kobe earthquake, an overview. On January 17, 1995, a magnitude 6.9 earthquake struck near the city of Kobe, Japan. Over 6,400 lives were lost. More than 200,000 buildings were damaged or destroyed. Infrastructure, including highways, bridges, and the city's port, suffered catastrophic failures. But beyond collapsed structures and fires, one factor stood out: the widespread liquefaction in reclaimed lands and waterfront areas. What is soil liquefaction? Liquefaction occurs when loose, water-saturated soils lose their strength during shaking and start behaving like a liquid. During strong seismic vibrations, the water pressure between soil particles rises. Soil particles lose contact and can no longer support loads. Buildings, roads, and pipelines resting on that soil sink, tilt, or collapse. It's like placing a building on top of wet sand at the beach. The moment waves hit, the sand gives way. Liquefaction in Kobe, where it happened. In Kobe, liquefaction was especially severe in reclaimed port areas. Much of Kobe's modern port was built on filled land, soft soils and dredged sand prone to liquefaction. Harbor facilities, cranes, warehouses, and container yards sank or tilted dramatically. Underground infrastructure, water pipes burst and sewer systems cracked as soil shifted. These areas were hit hardest, while structures on natural rock fared much better. Effects of liquefaction in Kobe. Liquefaction caused cascading damage. Foundation failures. Buildings tilted at extreme angles, some beyond repair. Port collapse. Kobe's port, one of the busiest in Asia, was crippled as quay walls slid into the sea. Transportation disruption. Roads buckled and underground train systems were heavily damaged. Utility outages. Lifeline services like gas and water were cut off for weeks. The earthquake was already deadly, but liquefaction multiplied the destruction and slowed recovery. Why Kobe was so vulnerable? Several factors contributed to severe liquefaction. Reclaimed land. Kobe's port was built on loose, recently deposited soils with poor compaction. High groundwater levels. Saturated soils were especially susceptible to poor pressure buildup. Soil type. Fine sands and silts are more prone to liquefaction than denser soils or rock. Urban density. Heavy structures in vulnerable zones increase risk. In short, human decisions, like building critical facilities on reclaimed land, intensified natural hazards. Lessons learned from Kobe. The Kobe earthquake became a turning point for geotechnical earthquake engineering. Key lessons included the importance of site selection, avoiding construction on liquefaction-prone soils where possible. Ground improvement techniques, using stone columns, deep soil mixing, and compaction to strengthen soils in high-risk zones. Seismic design of ports and infrastructure, updating standards for quay walls, bridges, and lifelines. Emergency planning, ensuring that cities have backup infrastructure when ports or utilities fail. Kobe showed that earthquakes are not just geological events. They're also engineering and planning challenges. Global impact of Kobe's case study. After 1995, engineers worldwide updated their approaches. Japan, nationwide soil liquefaction mapping and strict building codes. United States and Europe. More detailed geotechnical site investigations became mandatory in seismic zones. New Zealand and Asia. Liquefaction studies played a major role in urban planning, especially after Christchurch 2011 confirmed similar risks. Kobe's tragedy reshaped global standards for building in coastal and reclaimed areas. Challenges in preventing liquefaction. Even with modern techniques, challenges remain. High cost of soil improvement, not always feasible for large cities. Uncertainty in earthquake behavior. Soil response can vary from site to site. Retrofitting existing infrastructure. Much of the world's ports and cities are already on reclaimed land. Engineers today focus not only on prevention, but also on designing resilient systems that can recover quickly after liquefaction. The 1995 Kobe earthquake remains one of the clearest reminders that the real danger of earthquakes isn't always in the shaking itself. It's in how the ground beneath us responds. Soil liquefaction turned Kobe's reclaimed lands into shifting sands, crippling a major city and changing how engineers view geotechnical earthquake hazards. Today, thanks to Kobe, engineers are more cautious about where and how we build, especially on reclaimed or soft soils. It's a lesson written in tragedy, but one that continues to shape safer cities worldwide. Thanks for joining us on Blueprint to Reality. If you found this case study insightful, subscribe for more no-visual, all-value engineering stories. Until next time, stay safe and keep building smart.